Right, with a long gesture like this, it makes a long note, and a short gesture like this makes a short note. And other people say, it doesn't matter what you do after impact. You can wave your hands, you can dance around, the physics of the situation are done. So I decided to test this empirically, and I recorded this internationally acclaimed marimbist giving his best attempt to produce long and short notes. And so we'll have samples of these now, starting with the long. And here is the short. Whoops. And cross them. So now we've got that same audio, the long audio, paired with the long and the short visual. And this allows us to look at the perceptual consequences of the gesture independent of the acoustic consequences. And so these four things make up the audiovisual condition. We also had an audio alone condition where we just had the auditory information from the long and the short note. Now, in terms of the presentation of the experiment, participants just sat at a computer and we told them that the sight and sounds were mismatched and asked them to base their rating of the note on the auditory information alone. Now, this is actually a crucial part of the design because we know that a motion like this looks long and a motion like this looks short. And there's not a lot of interest in doing an experiment to explore that. What I want to know is, does that longer motion change what you're hearing? Does it make the note sound longer? And so that's why it's important for them to know there is a mismatch potentially and to rate the response based on the sound alone. Now, they made their responses after watching the videos, which they saw individually, not in a pair like we just did now. They made their responses on the slider. The slider has endpoints labeled long and short. The position of this nub on the slider after the end of the trial was translated into a number between 0 and 100, and that's what we'll use for the statistical analyses that we'll talk about next. In terms of the results, we're going to break things down into two separate discussions because first we have the results from the audio alone and then the results from the audiovisual. So on the y-axis here we have the duration rating, and that number just corresponds to the position of that nub on the slider at the end of the trial. And we have the ratings of two kinds of sounds, the audio from the long and the short gestures. Well, because I already told you that acoustically they're not any different, unsurprisingly, the sound from the long and the short weren't rated any different in duration in the absence of visual information. The interesting thing is that when we add in the gestures here, we can look at the ratings of the same sound when it's paired with a long versus a short gesture. And here we can see that the sound is rated considerably longer when it's paired with the red gesture, the long gesture in red, as opposed to the short gesture in blue. And we see this for the long audio and the short audio because, well, they weren't any different actually to start with. And so what we're seeing here is that while marimbists sometimes believe they're creating notes that are acoustically longer and shorter, the gesture actually fails to change the sound of the note, but it accidentally, without understanding it on the part of the performer, can change the way the note sounds for audiences. And so this is, I think, something that's useful to know from a practical standpoint. And I got involved in this in part because I was just wondering what are the things that I should be doing as a performer to connect better with the audience. And so there's a lot of practical musical applications. But what we're going to focus now is on what this means theoretically for our understanding of the way information is integrated across different modalities. So if we look at the literature on audiovisual integration, there have been many, many studies on this over a number of years, and the general breakdown goes something like this. If we're looking at conflicts in space, which is sort of the classic way of translating the ventriloquist illusion into a research paradigm, so I flash a light over here and play a tone over here, vision will capture the location of that event, so it'll sound like the tone is coming from the location of the light. That is essentially what we have in the ventriloquist illusion. So vision dominates spatial tasks because the acuity of the visual system is much better spatially than the acuity of the auditory system. Now, if we're talking about a timing task, though, then the story changes. The auditory system has much better timing acuity, so if we play a sound for 2 seconds and shine a light for longer or shorter, the duration of the light won't have much effect on the duration of the tone, but the sound will affect the visual duration. And this is because the auditory system has great temporal acuity. As you guys probably know, if you want to record CD quality sound, you'll be using a 44.1 standard typically, meaning you've got 44,100 samples a second, because you need information coming in at that rate to fool your ear into hearing the sound as if it's in the room. But if you want to fool the eye into seeing continuous motion, you need far less than 44,000 samples. In fact, 30 is what we use in the videos here. 18 is often perfectly adequate. So there's a big disparity in the resolution of the systems, and that maps nicely onto what we typically see in terms of the trade-offs. It's usually the better quality information that's dominating. But this is sort of perplexing because with the marimba illusion, what we saw is the visual information was changing our perception of the duration. And in fact, if I had known more about the literature before I did the study, I probably wouldn't have actually looked at that question, because it's all in very strong agreement that that illusion is not really possible. There's a number of reasons as to why that could be happening, and we'll go through some of them. If you just trust me for now, so it wasn't a response bias issue, an issue where the perception wasn't changing but the responses actually were. It is actually a real perceptual change, and the key reason for this discrepancy between what we found with the marimba illusion, what we typically see in research, has to do with the kinds of sounds that were being used. So a lot of these studies here are done with what I call the flat tone, which have the abrupt onset, the sustained period, and the offset. And when we assess the perceptual system for audiovisual integration using those flat tones, we typically see vision doesn't affect auditory judgments of duration. However, when we're using natural sounds like the impact sounds that clearly go with the impact gesture, then we saw something different. So this is why we started getting really interested in the role of timbre in general and amplitude envelope in particular. So for a second experiment to try and explore this issue, we took the same videos and paired them with different kinds of sounds. Sound of the piano, French horn, clarinet, voice, or white noise. And here's samples of those sounds now. Gotta have some white noise in there to make it a real solid experiment. Okay, so we took these different sounds and we paired them with the same original videos. So now we're going to see the marimba striking the instrument and hear it paired with these different kinds of sounds. So now we get some things that are a little bit odd. It's the clarinet paired with the marimba there, but I think my favorite one, and I really have hundreds of these videos lying around, is the impact gesture paired with the singer. This one, there's something that's clearly off about this. Oops. Huh. Including the laptop's performance of that. Let's try that again. So when we see this clear visual impact and hear a sustained sound like singing, it's pretty clear that the one doesn't cause the other one. So it seems a little odd to pair these things together that don't go together, but neither of these stimuli have anything less in terms of the auditory and visual component for the congruity than a tone beep and a light flash. So here it's just clear that one doesn't cause the other, and that's a very different experience that we have than when we listen to, say, the sound of the piano paired with these gestures. So here it's an impact sound. Now it's a hammer on a string instead of a mallet on a bar of wood, but it's in the same category of sound. So the experiment here involves 6 different kinds of sounds: the original marimba, and then the piano, the horn, clarinet, the voice, and the white noise. We used the same instructions here to be able to compare things. We told people the sight and sound didn't always go together. I think they would probably get that anyway, but we wanted to be consistent. So we said that, and we also asked them again to rate the duration of the sound alone, because we want to see, does the gesture change your perception of the sound depending on the kind of timbre. Now, because we have so many sounds, for the results we have a slightly different format. We have the 6 different timbres down here, and on the y-axis we're going to look not at the raw duration ratings, but how much vision influenced your rating of the sound. So it's just the rating of a sound when it's paired with the long gesture, and then subtracting the rating of that same sound when it's paired with the short gesture. We can see that with the marimba timbre. Once again, we have a big effect. So the note was rated about 8 points longer on this scale when it was paired with the long gesture as opposed to the short. With the piano one, which is our first manipulation, we get a sort of half-size effect. So here we still have some integration. But what's really beautiful here is that these 4 sounds here, where the gesture couldn't produce that sound, have no meaningful visual influence, because the error bars here are straddling that 0 point. Now, another way of thinking about this is that it's sort of a task in conflicts. You're seeing visual information, we're asking you to ignore that and just rate the auditory information. People are doing a fantastic job of that over here when the gesture doesn't cause the sound. When we have these sounds over here where the gesture either caused it or is somewhat plausible, I guess, in causing it, then it's actually not possible to keep these two things separated. And so it's showing how important this, the unity is between the different modalities, and it's not just the information quality alone in one modality as opposed to the other. But if we look now at the waveforms of the sounds, we can see there's a difference here between the piano one, which has that exponential decay, and the other ones which aren't really flat tones, but they have some kind of sustain. Now, one potential explanation is that actually because these trail off gradually, it's hard to know where the endpoint is, and because of that ambiguity, that's where we'll typically see information influencing from other modalities. We'll talk about that later, but that's not actually the core explanation for what's going on here. It's actually the detection of a link between an impact motion and an impact sound. Now, the reason we get this sort of half effect with the piano is that the envelope there is fairly similar to what we've seen when we strike a marimba. And so if we go back to the beginning, to the original illusion, here we're seeing this novel visual influence on an auditory duration judgment task. There's a lot of things when we look at the natural sounds that differ between the different instruments. Clearly you can see from the plot here the amplitude envelope's different, but also the spectral information. And so if we want to really control this and really test the role of amplitude envelope, what we want to do is now make sure there are no other variables. We're sort of like burrowing down to get more and more extracted from the original paradigm. But the next thing we did is take pure tones and just shape them with either an exponentially decaying envelope here or the flat envelope. But they're just sine waves in each case, so we have the same kind of auditory information, and now they're paired with long and short visuals. Here I used a pseudo point light display. It's just a single dot tracing the head of the mallet from each of the videos. And I'm going to show you now samples of the original long gesture paired with a percussive tone and then a flat tone. So that's the experiment here. We're just looking purely at the role of amplitude envelope. So the sounds are equated there on their spectral information. And we can see now, if we look at the results, on the y-axis again we have this duration rating. And what we're doing is looking at the effect of the visual information when it's paired with the percussive tone or flat tone. We can see that paired with the percussive tone, we get the same influence that we found before. The notes are rated considerably longer when they're paired with the long gesture as opposed to the short. But this is the ultimate test for what we're looking at in this paradigm, because there's many, many studies showing that vision shouldn't or doesn't affect auditory judgments of duration. And as it turns out, when we take the spectral information from over here and just put a flat envelope on it, now we get the same things that we would expect from a reading of the literature. So when we're using a flat tone, we're getting an outcome that's actually qualitatively different than what we see if we're using a sound with a natural envelope there. Now, like I said before, one of the potential explanations for what's going on, if you look at the optimal integration framework, is that the reason we're seeing this novel influence on a decaying tone here is that the offset point is ambiguous. And that's definitely true when you're trying to figure out exactly where that tone goes off. And I have this email exchange with a grad student where I had synthesized some tones for an experiment we'll talk about later. And I was saying, it's 760 milliseconds, and he's writing back, I think it's only like 755. And I'm saying, it's definitely 760 because I made it myself. And he's like, no, it's 755. I'm like, I'm zooming into the end of it on my sound editor. He's zooming into the end of it on his. And it turns out one of the sound editors just zoomed in a little bit farther at the end, which highlights the whole absurdity of trying to understand exactly where that note's going off. So the way we usually look at these kinds of things perceptually is just look at the ambiguity in the ratings and how consistent are they when we're rating either the percussive tones here or the flat tones. So the data over here is taken from a separate condition. It was an audio alone sample where people were just rating the durations of the sounds alone. And we can see here, if we look at the variability, we get no more variability when we're rating the percussive tones as opposed to the flat tones. And I did a similar analysis with the different timbres with the marimba, French horn, clarinet before, and we found a similar story where there was no more meaningfully greater variability in the ratings of the impact sounds than there were the sustained sounds. And so it seems here that this breaks with the framework of optimal integration because it's showing the importance, one, of the unity between the gesture and the sound, and then two, it's also highlighting that sometimes the conclusions and frameworks we get from running experiments with the flat tones aren't going to generalize to sounds with the more dynamically changing envelopes. Now typically when we study these kinds of issues, what we're doing is looking at how the audiovisual integration system is resolving conflicts. I think a lot of this comes from the ventriloquist effect. So we go with our paradigm here, we introduce a conflict in space, and we see what happens. Light flash here, conflict with the tone here, and then we localize the event as coming from somewhere in the middle. And that's a useful way of understanding how the perceptual system weights this different information, these trade-offs. But it's also important to think about what is the perceptual system actually doing in the real world. And so if you walk down the street, we might encounter a situation like this where you have a lot of different sounds and a lot of different sights. And the challenge here is for the perceptual system not to resolve the conflicts, but it's to find the unity. And we need to know which sound goes with which voice and which screech of the tires goes with which car. And that's a very different problem than resolving a conflict in space or resolving a conflict in time. And so I started thinking more about what is it that the perceptual system is looking at in order to find the unity. Because if we use a paradigm where we just manipulate everything and control everything and we only have one kind of conflict, then the perceptual system will give us some kind of lawful response. The question is, does that help explain the things that we're really interested in that helped motivate us to do this in the first place? And in fact, resolving the unity and resolving the conflict in audiovisual information is a really challenging task. And this happens effortlessly, which is why ventriloquists are able to exploit the perceptual system of the audience so seamlessly. And in fact, it's not just when we see these like parlor tricks with the ventriloquist effect. Your perceptual system is doing this frequently. For instance, every time we go to a movie theater, at least in the old days, before we had speakers, 18 speakers all over the theater, we'd have, say, speakers set in places on the side of the screen, and it sounds like the voice is coming from the face of the actors as they move around, but the speakers aren't actually moving. It's just the visual acuity the acuity for space is much better in the visual system, and so vision captures the sound, and so it would sound like it's coming from the location of their face there. And even right now, in a conflict-free situation, my face and voice are entering your brain through different sensory pathways, and it's a big challenge to try and figure out what goes with what. And in doing that, you're better served by putting the sights and sounds that go together, and not just the best quality sound with the best quality sight. But even though this process is seamless for most of us, the same thing can't be said for individuals who are suffering with autism spectrum disorder. So there's a number of deficits that kids and adults who are dealing with this are struggling with. One is this challenge of gluing together the sights and the sounds that go together. So Laura Silverman is an autism researcher who specializes in audiovisual integration of speech at the University of Rochester. And she got involved in this project in a very roundabout way. So a few years ago, when she joined the faculty there, another member who just joined the faculty was the marimbist that I used in the study here. So Mike Burritt was a percussion professor at Northwestern when I did my graduate work there. He got hired away to Eastman a couple years later. The same year, Laura started at the University of Rochester. So they met at a new faculty dinner. He said, hey, come check out my recital. I'll be doing a bunch of marimba pieces. Like most people, she had no idea what the marimba was. So she decided to go check it out. She was blown away because he's an amazing performer. And then one day she was sitting there procrastinating while writing her grant application. And she was trying to find an audiovisual integration task that didn't involve speech, that used some natural sounds. And she just, on a whim, typed marimba and perception into Google and found some of the papers that we did. So I get this email out of the blue saying, hey, do you want to collaborate on this study to look at audiovisual integration in kids with autism? And I thought, that sounds like a really interesting thing. But I don't really know anything about the whole sensory integration disorder literature. So she started sending me some things, and I was learning. There's a number of deficits that we often see. It's a difficult thing to study because the symptoms aren't presenting the same way in each person, but there's this characteristic pattern where we often have these problems with eye gaze and facial expression and challenges with gesture while communicating. And another challenge that we see a lot is that for a lot of the kids, sticking together sights and sounds in the way that other adults are doing becomes much more challenging. And this produces a lot of issues for social communication because these gestures are very important in speech. And also just seeing the lip movements that I'm using helps you understand the speech better. So we got really interested in how audiovisual integration happens in individuals on the spectrum. And if we look at the literature, there's sort of two different stories. The first one that's fairly clear is that if we're talking about something like speech, there's consistent reports of deficits across a wide range of tasks. Over the last 10, 12 years, there have been a number of studies, though, looking at audiovisual integration in this population, just with what's called the tone beep light flash stimuli. And here, a lot of times, they're actually integrating just fine. It's a little murky. There's somewhere there are problems, but it's pretty clear there's problems with speech. There might not be problems with the beat flash world. And so what's interesting to me is that speech is this complex auditory stimuli with lots of temporal variation, whereas the beat flash studies are basically using, sounds with very simple temporal structures. And so the question is whether these deficits are maybe generalized audiovisual integration deficits, or they could actually be specific to speech. And targeting therapies and helping to devise treatments, it's useful to know which level that we're looking at. So Laura got an NIH grant in R03. We got $300,000 to study this over 3 years. I was super excited when this came in because I thought, this is great. I've got 9 experiments queued up. There's all these great things we can do. And then she said, no, actually that reward will cover 1 study because it takes so much time to recruit this population, find the age and IQ match controls. So we have 1 shot here at doing this. So she was able to recruit 24 high-functioning individuals on the spectrum and 24 controls, matched all these parameters. Once again, we told them that the audiovisual information didn't go together, and we asked them to rate the sound alone. We showed them the videos one by one on the monitor. We tweaked the wording slightly on the questions because the age was much lower here. I think there were 14 to 18, but it's basically the same kind of paradigm. And so what we found here, again on the y-axis, we have these duration ratings, and now we've got the long and short gestures here, but presented to the controls and the kids on the spectrum here. And what we can see is that with the controls, once again, we have the illusion. So the same sound is rated longer when it's paired with a long gesture as opposed to a short gesture. And for the kids on the spectrum who have problems with certain stimuli in terms of the integration, we're actually seeing they're doing just fine here with the integration. So the magnitude of the illusion is no different here between the 2 groups. We're not entirely sure why the ratings are so much shorter here. And that happened across the board, both for the gestures alone, the sound alone, and their integration here. They're rating them shorter, and so we're talking to some of her colleagues now and trying to figure out what that might mean. But in terms of our initial question about looking at when we see these deficits in speech, but we don't see them in the beat flash world, I think this is helpful because it clarifies that if we go somewhere in between with this naturalistic task with biological motion and time-varying sounds, we're still seeing integration like we do in the typically developing population. So definitely amplitude envelope is playing an important role, and what we're doing now in my lab is looking at a number of different situations where it can help us refine our understanding of different theories and processes. And so there's 3 project areas that I'll go through briefly now to summarize what we've done recently. The first is looking at duration processing strategies. We're interested in why it is that the percussive tones don't seem to be more ambiguous than the flat tones, given that we have those long offsets trailing off. The second one is a project looking at what's called the unity assumption or the identity decision. And this is that decision the perceptual system often has to make as to decide what sites go with what sounds. We're finding some really interesting differences between sounds with, say, flat envelopes and percussive envelopes, or in some cases, interesting things that come when envelope is not really controlled for in an experiment. And so the last thing that I'll talk about is this ongoing project where we're actually doing a survey of the sounds used in auditory research to try and understand and establish a baseline for what are the kinds of stimuli that we're using in all these experiments that help us derive these theories and these models to understand what the perceptual system is doing. So the first experiment is looking at duration processing strategies. And here the key thing we wanted to test is what happens when we take out this sustained period. So we're designing this around the idea that because the variability was no different when we were using the percussive tones versus the flat tones in those earlier experiments, is it possible that with the percussive tones, participants are using what we call a prediction strategy, where you're predicting the moment of offset based on the slope? Over here, that kind of strategy would be impossible because there is no slope. And from listening to this tone, you don't know if it's going to be 50 milliseconds or 500, or it could go on for an hour because there's no information about when that will end. So here, I suspect folks have to be using some kind of elapsed time strategy where you mark the beginning and the end and calculate the difference. And that fits with a lot of different frameworks and models for timing in terms of the way it's assessed in the literature. So for this task here, we had 2 basic kinds of sounds. You have the flat tones and the percussive tones. And the task is fairly straightforward. We just play the standard and the comparator and ask people to respond which one's longer. So in a trial, you might hear something like this. Say which one was the second tone longer than the first, or on a percussive trial, you'd have this. So we used the durations in a number of different ways, but to start off with, we just used the same acoustic duration for each of the sounds here. The structure of this one is somewhat dense, and so we've got all the information in an article we published in Perception in 2014, but the overall gist is this. So we had a situation in which we blocked these matched trials here separately. So you heard either all the percussive ones and then did all the flat ones. The other extreme was we had a block where they're completely interleaved over here. Now we actually had matched and mismatched trials as well, but for our purposes what we're interested in is just how people are doing on the matched trials when they're presented either blocked like this or mixed and interleaved over here. So in this situation, you know what kind of sound will be coming up, and so if you have a better strategy to use, say the prediction one for the percussive tones, you're able to use that, and you can use the time-elapsed one here. In this situation, you have no ability to predict what kind of sound you'll be hearing, and so this precludes the ability to use the prediction strategy, because the prediction strategy fails completely for the flat tones. The elapsed time strategy could work for the percussive tones, but we'd expect to see worse performance because it's hard to know where those percussive tones are off. So those are the two extremes, the things that we really wanted to test. We had this intermediate condition where they're all matched trials, but the trials themselves are randomly ordered. So here you can actually, you know ahead of time before the second tone starts what kind of sound it will be because it matches the first. Over here you have no ability to predict anything. And that's what we want to really see are the extremes here. So in terms of the results, we see here, we're just looking at the slope of this psychometric curve as an index for performance. And the key thing is we want to see what happens for the two kinds of match trials up here when they're blocked separately as opposed to over here. Now when they're blocked separately, meaning participants can choose the prediction strategy when it's appropriate, they're actually doing just fine with the percussive tones. Over here is where we see a difference, where the performance of the percussive tones is actually worse than the flat tones, because here participants aren't able to switch over to the prediction strategy. You're stuck using the time-elapsed strategy because that's the only one that can actually work for both tones. It's just more problematic for the percussive ones, which is, I suspect, why we're seeing the worst performance there. Over here, for the ones that are randomized within a block, it's somewhere in between. And so this is helpful in clarifying what we were seeing earlier with audiovisual integration, because it's the first bit of evidence, and we have to do some more work on this, but it's the first bit that's suggesting we might have fundamentally different ways of listening to tones that are flat versus percussive. Yeah?
Can you go back to the previous slide?
Sure.
I was confused. I didn't see any mismatched pairs here.
Yeah.
But you are doing mismatched pairs. And is there an image where you superimpose the percussive sound with sustained sound so we get a sense of what strategy is being used over?
Yeah, wow, that's great detailed looking at the slide there. So there was so much stuff, I tried to simplify it by taking the other ones off the slide. So the full experiment, we had a condition where everything was interleaved, including matched trials and mismatched trials. What we're looking at on the next figure was just the results from the matched trials, because they did much better when they were matched as opposed to when they were mismatched. So if you look at the curves right by one another, that's not at all surprising. So we took that out for this image, but all the details are in the paper if you want to see all of it. Great spotting that. Okay, good. Wanted to make sure everyone was awake, so that's good. Okay, so got that there. Okay, so this brings us to a newer one. This is the last sort of new perceptual data set here. So we've looked a lot at differences between flat tones and percussive tones. And I think a lot of times, if we're just using the flat tones, we're not going to see some of the interesting processes that the perceptual system is using. As a different way of looking at this, there's this literature on the unity assumption where we find something really fascinating when we look at amplitude envelope as an important parameter here. There's a fantastic paper a couple years ago. Vaticus and Spence did this neat thing where they paired gender-matched and mismatched faces and voices. And they wanted to look at the role of congruity in triggering this unity assumption, or it's been called the identity decision, the idea that sights and sounds go together. So they paired faces and voices, and then they looked at how far apart they had to be before you lost the ability to tell the order, a good way of indexing when they were bound. And so what they found is that when there was congruity, so you had a male face and a male voice, there was stronger binding than we had no congruity. It seems sort of intuitive, but this is actually a really nice finding because it was a very controlled and rigorous way of looking at this issue, which hadn't always been done to quite the same level of rigor, and so it gave us great confidence that we see this process happening. So they found this with the speech, and then next year they followed this up with musical stimuli. And so here they used a note on the piano or a note plucked on the guitar. What they found here, though, was surprising because now the congruity stopped playing a role. And we saw the same level of binding when you saw, say, a finger plucking a string when it's paired with the piano note, as opposed to when the things actually go together. And so they followed this up with some other non-musical things like a hammer hitting a block of ice and a ball bouncing on the floor. And they found the same thing again, where the congruity didn't seem to matter. And so they concluded based on this and some other things that the unity assumption doesn't apply to these musical stimuli, these other non-speech stimuli. And that fits with the literature on the speech is special hypothesis. And so it's been widely cited, and it makes a fair amount of intuitive sense, except a couple years ago when we were going over this in a lab meeting, one of my undergrad students was talking about this, and we were thinking about the envelope stuff, and he was saying, but actually, if we look at the amplitude envelopes of the piano and the guitar, they're actually very similar. So they both come from energy being introduced to the system and then gradually dying away. And so maybe the reason why they didn't find the congruity here is that the amplitude envelope is actually signaling that both of these things go together, sort of like when the guy hit the marimba and you heard the piano sound. And if you think about these other things, the hammer on the ice and the ball being dropped, once again, they're impact sounds, so the amplitude envelopes of the sounds are going to be similar. So these are the sounds here. We wrote to Vaticus and got a copy of those, and here I'm assuming they'd be fairly similar as well. So for Lorraine's master's thesis, what we did is we just recorded single notes on the cello or on the marimba, because these have very different envelopes. And so here's what we've got here for the single note on the cello. Now this is an example of a mismatch condition, which I'm sure you'll notice. The gesture that this marimbist is using does not really naturally produce the sound you'll hear. Okay, so the question is, now that we're controlling, or at least using different envelopes, are we going to find novel evidence for the unity assumption in this non-speech task? So the basic trial structure is fairly straightforward. We got the cello sound and the marimba sound, and each one's paired with the cello gesture, marimba gesture, so we got the matched and the mismatched trials. We used the same offsets that they had in the original paper. We did the same kinds of analyses. And what we found here, on the y-axis, we're looking at the threshold for achieving that just noticeable difference. So essentially, it's a fancy way of saying we're looking at stronger binding up here and weaker binding down here. And what we find is when we look at the match versus the mismatch, we get very clear evidence for the unity assumption in this non-speech task. And so this actually was just accepted last week to Attention, Perception, and Psychophysics, so hopefully that'll be out pretty soon. And we think it's a neat finding of what happens when we're looking more carefully at the role of amplitude envelope. And if we unpack this a bit more, we can look not just at the matched and mismatched, but how these things actually line up. And so we've got the sounds here. Oh, there we go. So we've got the cello sound and the marimba note there, and then we have them paired with the different kinds of gestures. This is the same data that was then collapsed in the slide before. But when we pick it apart, we can see that we have this effective congruity here. So there's stronger binding when the cello sound goes with the cello movements. And then over here, we get stronger binding when the marimba sound goes with the marimba movements. But what I think is really surprising, and I did not expect this at all, is that the cello envelope is more gradual in the onset, and the motion is a lot less clear where the onset is as well. I mean, you can't be any clearer about where the downbeat's coming than a motion like this, which is probably one reason why conductors will use those kinds of motions. And same thing with the onset of the marimba sound, it's fairly abrupt. But over here you can see there's actually, it's no harder to do the task with the cello sound and the gesture than the marimba one with the marimba gesture. And so I think it's suggesting that the detection of unity is so powerful, it's actually overriding what we might expect just based on these pure low-level characteristics of the stimuli by themselves. So there's more that we want to do with that, but Lorraine graduated, so we sort of tied a ribbon around that and set that up as that one paper there, which brings us to the point of looking at sort of what we've uncovered so far. So if we step away from this study here, which is using these nice natural sounds of the cello and the marimba, and go back to sort of the more traditional sounds, if we're looking at literature and audiovisual integration, we see a very clear story about vision not affecting auditory judgments of timing, and that seems to apply very nicely as long as we're using these flat tones. And we can look at a lot of the theories about duration estimation. They seem to apply very well if we're using tones where you're not able to make any kind of prediction about where the offset is happening. But we've seen if we use a different kind of structure, like pure tones just shaped with these exponentially decaying things, we see something very different. And so I think it's an interesting thing to stop and contemplate then when we find some interesting phenomena like the ventriloquist effect, or like for our lab we're often interested in something natural like music. When we try to pick this apart and study it, we want to control these variables, because otherwise we don't really know if what we think is happening is really happening. But by doing that, we sometimes introduce different challenges where now what we're finding here might not actually tell us that much about the thing we're really interested in. Because in the end, we're not really that excited about how people hear tone beeps in a sound booth. We're using that setup to try and understand these interesting and rich phenomena, whether it's the ventriloquist effect or music or rap, like you guys are doing in Takako's lab. So this got us wondering then, what exactly are the kinds of sounds that we're using in auditory research? I suspect we're using a lot of flat tones, but suspecting and knowing aren't really the same thing. Actually, they're not at all the same thing. So we wanted to actually do an empirical analysis and try and figure this out. So a couple years ago, Dan Levitin and Anna Tiravolis published this interesting bibliographic summary of all articles published in music perception up to that point. They generously sent us the spreadsheet, which gave us a head start on this project that I'd wanted to do for a long time, which was go through and survey the kinds of sounds that we're using in auditory research. And so we figured at the outset we classify things into categories like percussive and flat. So anything like a cowbell, bongos, chimes, obviously those were percussive. Other things like hand claps or any kind of impact sound went into the percussive category. There's a wide array of flat tones. I now have a lot of information about this. So you have all kinds of flat sounds. The place I think you might hear these are like the emergency broadcast system test with a beep. And so it's interesting because I like to use images rather than text, and I wanted an image here to represent these sounds. So for the percussive ones, it's easy to do that. For the flat ones, I don't think there is a real world thing that makes this kind of sound, which is just the point we'll come back to. We have another category here, which we started off with, it's just called other. It was pretty broad. So we got a lot of different instrument sounds because it was music perception. We had some things like this. We called them pyramid tones. We've had a lot of fun with coming up with names for different kinds of sounds. And so all these went into the other category here. So that much, I figured, okay, this will be a pretty straightforward project. The problem is we needed a fourth category. And this was not something that we anticipated at all at the outset. So I figured we got these three categories. I was working with an undergrad student at the time who was now doing a PhD in audiology. And he kept coming in each week to our meetings and saying, well, I classified these, but a bunch of them they just don't actually say. And I was like, Johnny, you have to go back and look more carefully because it's going to be in there. And he's like, no, I'm really not seeing it. So we would go through 10 of these per week in painstaking detail to extract the amplitude envelope information. And what I realized is we needed a fourth category that we called undefined, because a lot of articles actually didn't give definition of the temporal structures of the sounds they're using. We'd have elaborate information about the spectral information, the duration, and all these other things, but then we'd just have, let's say it was like a 500 millisecond tone. So I suspect a lot of those are flat, but a lot of times we actually didn't have definition of the amplitude envelope.
Maybe a dumb question, but in this other category, I see both synthetic sounds, very artificial, and real instrument sounds, and I would have thought those would be in separate categories.
That's a great question. To start with, we did it like this. Later on, we've been separating it for that exact reason, because I want to know the percentage of natural sounds and unnatural ones. Yeah, this project sort of took on a life of its own. Originally, it was actually something we could do because we didn't have the sound booths yet. We were still setting up the lab. But now it's been years later and we're still not done with it because of those kinds of reasons. Okay, so we went through and we had these four basic categories now. We just tallied them up, and the story was actually pretty surprising. So in the end, I thought we'd find the most flat tones, but our biggest category is actually undefined, where we don't have information about the temporal structure of the sound. Now, that wasn't something that was anticipated at the beginning, and I'm not really a betting man, but I would bet heavily that everything in this undefined category was actually flat. These were really interesting research studies done by some of the top researchers in the field, reviewed by other researchers, and I suspect if the envelopes were moving during the tone, then they would have said this in the paper. And so if they just said it's a 500 millisecond tone, I suspect it probably was flat. We didn't want to just assume everything was flat because we don't actually know if you're trying to replicate that, then you wouldn't actually be able to make the exact same sound. So some of the feedback we got after publishing this, and actually in music perception, from some folks outside the field of music was that, well, maybe you just have this lower definition because it's only a music journal, and it's not really that rigorous. So have you tried looking at this with a more, rigorous journal outside of just doing musical stuff? So we decided to extend the survey, appropriately enough, to attention perception and psychophysics. So we went through, this was about 100 papers, it was like 212 studies. It takes a while to go through and pick this apart for every sound that we've got in there. The APP one was even more because we did 2 or 3 articles per year for the length of the journal. Went through and split them apart according to a number of different metrics, and we have really detailed information about all these different properties of sound that are being used in studies now. And what we found with the APP survey was actually things were a lot worse in terms of the definition. So now it's over half of the sounds have undefined amplitude envelopes. Now, for the most part, these are papers where we have very high specification levels for things like spectral structure, duration of the stimuli, the exact model of headphone that's used to deliver the sound. Like that we generally have specified, but the amplitude envelope wasn't something that we really thought as a field was all that important. Now, in the end, I think the undefined thing is sort of an interesting gotcha moment, but that's not really the important thing about the survey. I think let's go ahead and just assume the undefined ones were probably flat. I think the more important thing is that if we lump them into this presumed flat category, we have the majority of sounds, like 85%, 86%, are using these flat amplitude envelopes. And now we started breaking it down into more refined categories. And so we've got clicks and click trains over here. And when we break down the other, about half of those were unnatural sounds too, just like those pyramid tones as opposed to a dog barking or something else. So the bottom line is it's like 91% of the sounds in this randomized sample from 2 top journals in perception are using sounds that don't have the kinds of amplitude variation that we find in musical sounds or other natural sounds. And so this is important because when we looked at audiovisual integration before, we have a whole framework that talks about different trade-offs that doesn't generalize to things like the marimba illusion where we're using these natural sounds. We tested that in a sort of head-on assessment using the pure tones shaped with the decaying structures, the flat structures, and we found again we get the integration with the natural sound but not with the flat envelope sound. So if most of the research for this kind of issue is based on one kind of sound, the question is to what degree will that generalize to the other kinds of sounds that we're interested in. We looked at these duration timing strategies and we saw some differences here between the flat tones and the percussive tones. And then as an interesting case study, and when we move out over to natural sounds, we saw this research on the unity assumption, which is really interesting. But when you don't look at the role of amplitude envelope, it can again sort of suggest some conclusions that don't necessarily generalize more broadly. So I think there's a tremendous amount of interesting work to be done in the future with looking at amplitude envelope just by itself with these pure tones shaped with the different structures. One of the comments I got in the reviews for the music perception survey was, well, you've surveyed 222 different experiments. Which ones in particular would turn out differently if you ran them with percussive versus flat tones? I thought, but that's actually an interesting question. I hope we don't have to run 222 experiments before we can publish this paper. But it's an open question. I'm sure there's some things that will turn out the same when we use the different kinds of tones, but I'm sure there's other ones that won't, like the ones that we've shown here. And so I think there's just a lot of interesting work to be done varying these tones and trying some different paradigms with that. And so we could spend the rest of my career just doing amplitude envelope replication studies, and that would be useful, but I think a more interesting thing is to just see what other people would like to do and explore. So I put together, appropriately enough for this group here, a Max MSP patch that I used originally to generate some of the sounds from that duration assessment experiment. I thought it'd be interesting to just put this up online, so you can download it now, and I'll show you where in a minute. But here, it's nothing groundbreaking from a Max patching standpoint, but I was using those music tech skills from back in the Northwestern days. But you can just specify what kind of frequency you want by typing it into the box there. If you'd like, you could use the piano keyboard to select that as well. And now you can listen to flat tones of whatever duration, or percussive tones. Those are some durations we used in an experiment, but you can type in whatever ones you want. So if there's any kind of question you'd like to explore, it's very easy to do. You don't need a license for Max here. You can use the runtime version and download that and run that. Something else we've done is also manipulate this, and rather than looking at the pure tones, use different sound files. So if you can choose that option, you can load in whatever file you want. And then create different kinds of shapes. So we use that for this experiment looking at auditory alarms in medical devices, which is an area that I'm really interested in exploring some more in the future. And so I think it's a useful tool. You can make percussive and flat sounds in MATLAB, or we've done some other ones in R. But I just thought as long as we've got this, it might be nice to give people the option of making those fairly easily. So if you're interested, just visit our website at maplelab.net. If you go to the software page, you can download that and look at some other programs we've been working on. You can also learn more about this research. If you go, we've got here pages on all the different projects that are happening at the moment. And you can see even on this amplitude envelope page, you can get your very own copy of this wonderful figure that I've been referring to back in the talk. I think it's interesting I'm trying to get more and more of the lab research online with these plain language explanations because I think it's an interesting way to interface with the public. And so we've actually done from a totally different project, but it's a new tool that we've got up online now that I'm excited about. We're really interested in the music of Bach and different interpretations and different tempi. And this comes from a separate corpus analysis study that we just published a paper on in Frontiers a couple months ago. And so as a result, we had to gather all these different scores from Bach to look at what the real timing information was because he didn't give us the metronome markings. And so we built this tool mostly to help us with some research, but I thought other people might find it interesting as well. So if you go to the website, you can just see all these different tempi, and you can select any kind of piece you want here from the set. So you choose like one of the major preludes. Let's go with C major. And now you can see the score. You can see all the different tempi that people have recommended. These are 7 different editors that, that Palmer sort of put forth. And you can see for all these different pieces, you can either select it there with the piano tool or in other different ways. Yeah, and you can see here the different tempi. 72, we got 76. You can also, if you want, flip over to attack rate, which is basically like note density, and I think that's a useful way of looking at things because sometimes the two of them aren't quite as in agreement as you'd expect. We've got a little bit of information about the editors, and we'll add some more on later on, but it's a neat way to explore this data set. So we've got a couple tools like this that we're working to put online, and so I encourage you to visit this if you'd like to learn more about Bach. Oh yeah, and you can also see all the different scores from some of these different editions, just because we had to gather them up to look at the tempo markings. Then I figured that'd be sort of a neat thing to share with other folks. So yeah, that's what we've got in terms of that. That ties into this whole big corpus study and communication of emotion project that we're doing right now. Just for some other things that we have going on, we're looking also a lot at sensory motor integration and how movements that musicians use or audiences can help improve our listening to rhythms. And we're doing a new project now where we're looking at interpersonal synchronization in this piece called Drumming, where we have Steve Reich wrote for musicians to start synchronized and then one gradually moves apart until they resynchronize a beat later. It's sort of the backwards way of looking at interpersonal synchronization. It sounds like the most unecological, non-musical thing ever, where you get expert musicians looking at one another while trying to not play together. But it's actually taken from a very important piece in the repertoire, and that's done in conjunction with Russell Hartenberger, who is actually a member of the Steve Reich Ensemble and premiered the piece in 1971. And he just thought it'd be interesting to look at this, and I thought that was really cool. So we're trying to work on that now. So I just want to acknowledge all the funding agencies that help to support this work. There's a lot of infrastructure and tools and everything that goes into that. But I think the most important part of the Maple Lab, or really any lab, is not all the gear, but it's all the people. And we have a small army of students that have been contributing to all these different projects. We've got Jess Gillard, who's done a lot of the work on the survey stuff. Johnny did the first survey in music perception years ago when he was an undergrad student. And Lorraine did the paper that's going to be in AP&P. So we've got a lot of interesting stuff going on, and there's information about all the students on the lab website. So finally, I just wanted to thank Takako and Madeline for inviting me out. It's an honor to be here at Stanford and visit CCRMA, and I had a great time in the lobby just leafing through all the booklets yesterday and like playing around with the toys down there. So that's a great way to welcome people to the center. So it's been a real joy to be here, and I look forward to answering your questions now from folks here or folks that are beaming in online. Thank you very much.
Nobody's asking now. That's the no. So I got to run out of it. It's a small point, but I was confused about what you said about the piano versus the guitar, because I expected it straightforward, that they both have similar envelopes and they're going to be easily confusable. But that's not what you said at first. And so what was the story? Because I heard you said this, and then it was surprise we said that.
So when Vaticus and Spence did the study, they wanted to take it out of the realm of speech and use some non-speech musical sounds. So they picked events that seemed different, and they used the piano note and the guitar pluck. Turns out the amplitude envelope was similar, but those were the events that they chose to use. So when we saw that That was the sort of seminal study looking at the unity assumption in the non-speech literature, and we thought, here's an interesting opportunity to look at the envelope. Yeah, because I agree, like musically, they seem pretty similar. Yeah, this is why we need more musicians doing music perception research, I think. These kinds of things, there's a lot of really interesting issues there.
On that note, who were the participants? Were they musically trained?
Good question. So for which study in particular?
The same one, I guess. I'm curious overall, actually. How you
That one, it was the good old Psych 101 pool, the 18 to 21 demographic that we know more about than anyone on Earth. We did get information about their musical training, and we are looking at some of the correlations there to see what degree expertise plays a role. And that's something that we're starting to get more involved with, partly because we're looking at some expertise things in the rhythm and timing stuff as well. So the first study I did with the marimba stuff was at Northwestern. Those were all music students who were encouraged to participate in the class in return for extra credit. Ever since then, it's mostly been psych students. And yeah, there are some interesting issues about how does expertise play a whole role in this. Yeah.
It seemed like if you're really used to doing synthesis with different types of envelope attacks and oscillators and stuff, it may offset some of those.
Yeah, that would be really interesting to look at. I mean, I also find, like, I'm an audio geek, and like I'll listen to sounds and certain, like whenever those trucks are backing up and they play those like flat tones, and like I'm in a frothy rage and no one else seems to really care. So it definitely, the training affects you with that. So that would be a neat thing to look at for sure. Yeah.
Thank you. Yeah.
I have a question.
Yeah. No, so do I, but go ahead.
Oh,
I was thinking.
then after you.
Okay. We also had a request to repeat the question that's asked, so that way I hear better. You can't hear me very well. But I wanted to know if you were interested at all in trying to see if longer gestures are particularly influential in making a note seem longer, or rather a shorter gesture. Because I noticed in your first study, which I think was your dissertation, it was one of the first slides. The length of listening to the sound, the perceived duration of the sound alone was pretty much the same as a long gesture, versus the short gestures seem to shorten the perceived duration a lot. And so I just didn't know if that was a pattern that you were noticing, that long gestures tended to influence it more than short, or...
Yeah, so the question is then whether, if we start with the baseline of the note, does the long gesture make it longer and the short gesture make it shorter, or is it something, I guess, more complicated? It is something more complicated. So with the notes that tended to be fairly long, then the rating of this note in isolation was similar to the rating of the note when it was paired with the long gesture, and the short brought it down. For the ones that were on the shorter side, it was the longer one that brought it up. So it's an interesting question. It's hard to answer from this because it's subjective rating of the duration. And so to look at that kind of thing, I've thought about doing some things where, like, press a button and release it when you think the note is off, and then we could get some kind of index of at least their perception of the absolute duration of it. And I think that's needed to answer that, because right now all I can say is that it depends a lot on where the note is in the scale. We have done some things with the dots, because you can pick apart the gestures and manipulate them in interesting ways, where we took the beginning of the long gesture and paired it with the end of the short gesture. And so you can move it all around. And so I do know from doing that it's the post-impact motion that's driving this. The pre-impact motion doesn't seem to matter. So we have start with the long and end with the short, compared to start with the short and end with the short. And it's the motion after impact that matters there. And it's actually the duration of that motion, not the velocity, the jerk, or the acceleration, because we manipulated all those as well. Which is sort of nice, because then it's a visual duration that's influencing auditory duration, which is one of those moments where it's like, oh, yeah, that sort of makes sense. But it makes sense after, spending a couple months in the weeds making all those. Yeah. Yeah.
Was there any correlation between frequency of the sound and binding?
Good question. So the question was whether there's any correlation between the frequency of the sound and the binding. With the cello and the marimba, we just had one in that study there, so we can't look at that. With the original marimba study, I had 3 different notes at different pitches. The main reason we did that is that the big bars ring for a lot longer than the short bars for the higher pitches. So the influence was the same across each of the pitches there. So I suspect there isn't a difference there, although you've got the duration sort of in that as well, but I wouldn't think there would be. Yeah. Yeah.
So I have 2 questions. The one is, have you tried to ask musicians percussionists to make longer sound or shorter sound, and then what happened to them in terms of gesture? Or do you think it might make difference in gesture? So that's the first question. So then the second question might be a little more complicated. I'm interested in hearing your speculation about why then the prediction of the length, that's really interesting. So why then people use percussive tones to mark IOIs, not really duration type of musical expression to, so physically speaking, that cannot produce sustained sound.
Okay.
For the longer duration, so you have to do tremolo like you said.
Yeah.
Right? So, is there? Can you speculate how human perception would work differently to perceive the timing or temporal information that fundamentally sets apart the percussion sound?
So, okay, I'll start with the second one because I've forgotten what the first one was. So for the second one, the question is speculate on why percussive sounds are often used in experiments where IOI is important when they're quicker, and I guess the duration sort of ramps off. I'm guessing it's because along with the duration ramp off, you get a very crisp onset, and I suspect percussion instruments have the clearest definition of where that beat is. So the perceptual center issue can be challenging with certain other sounds. So I think percussion sounds are good for that. I mean, sort of from a musical sense, like with the drummer, where they're putting that time is usually where the rest of the group is going. And so I think if people are thinking about a rhythmic task, then it makes sense to use percussive sounds there.
Is that only because the onset is so crisp? Is that only the reason that we want to use percussion tones for, marking? Or what happened to the prediction part,
Okay.
Can you say, you know what I'm
So then, I think in those kinds of tasks, what we want are, say, the metrical framework that comes out of basically where the onsets are. And the duration of the tone isn't as important there. It's just that it's a clear onset. So I suspect in that situation, all that matters is just sort of the one part of it, not the other. That's my guess. I don't know if you have a thought. So, so for the first question about if we ask musicians to try and play long and short notes, what kinds of different motions would they use? Well, that's actually where the whole study came from, in terms of I asked this internationally acclaimed marimbist to produce his best long and short note, and then we got those gestures that he made. It would actually be interesting, I was thinking as you were talking about that, to bring people into the live lab, get a bunch of percussionists and ask them to play in different ways, and then we could motion capture them and look at how the movements change. And so I will have to think more about that and maybe talk about that in the future. Yeah, or maybe next week when you're back on campus, Master. Yeah.
We've looked at sounds that are very stereotypical,
Mm-hmm.
the percussive sound and the sustained sound. But I wonder if you experimented, maybe by manipulation, with sound that are somewhat in between. Take a natural percussive sound and put on it an envelope that modifies some of its onset character, but it's natural afterwards. Or conversely, you can put an envelope on a sustained sound such that it sounds more percussive.
Yeah, I would love to do that. There's a couple of interesting experiments I have in mind where it sort of relays on or rests on building a continuum between the two kinds of sounds. It's hard to find in terms of the natural world, but it's possible in terms of the manipulation. What we have done is separate the amplitude envelope from the spectral information. We took white noise and filled like the marimba and the cello one to take that part out, but we haven't sort of gotten to manipulating just the envelope alone. I suspect folks here would probably have a better sense of how to do that than I do, but it seems like it would be doable, and it would be neat to have a continuum and look at integration sort of across these different characteristics.
That's partly because we also have a model of source. What can create that kind of sound?
Yeah.
And it's not just the envelope. And so that might take apart what comes from the envelope and what comes from the nature of the instrument.
Yeah. Yeah, that's a great point. Bill Gaver did some really interesting work in the 90s where he talks about what is it that we hear in the world. And he makes this fantastic point that when we listen to like sounds, and he played people sounds and just had him talk about it for his dissertation, people would say, they never said like, oh, that's a dense burst of noise with lots of energy in the mid-range. You play them a sound and they, what is that? And people say, it sounds like a book dropping, or it sounds like a car sort of moving up behind me. So when we listen in a natural setting, it's often for the events and the objects in the world. And then when we study in the lab, though, tend to be properties of sounds. Higher pitch, lower pitch, longer duration, shorter duration, because those are the things we can manipulate. But I think it's really interesting to contemplate how these things connect with source. And I know, like in a lot of musical composition situations, you want to get away from the source and for whatever artistic reasons. So in that situation with these manipulated envelopes, that would be something that we could do. I think that'd be very interesting. I think I forgot to repeat the question, I just realized, but it was a good one. Sorry.
I think the results would be different if you were to use artificial visualizations of, let's say, a ball dropping and flattening versus a human and something.
Great question. So would the results, I assume, of the audiovisual integration stuff be different if instead of the natural impacts we used other kinds of motions? I am quite sure if you took the visual and made it something that didn't look like an impact, then the integration would fall apart. We've done a couple things on that front. With the dots, we can manipulate them in interesting ways, and so we did one where instead of bouncing off the bar, he moves through the bar. So basically you take all the movement after impact and just sort of reverse 180 degrees. So pixel for pixel, it's the same amount of like acceleration of velocity and everything, but you just don't get the impact sense. And there's no integration. And it just looks like this weird dot speeding up and moving down. So I suspect if you just used a box moving in a certain way, it would go away as well. Because I mean, envelope is the important auditory cue, but the bigger overarching thing is that the unity matters a lot. And so anything that messes that up is going to weaken the integration. So we've shown that with the timbre stuff, like I showed here, where you use timbres that don't go with an impact event and they don't integrate. We did it with that through the bar one as well. We did another manipulation in the JEP, the 2009 article, where we took the temporal synchrony and manipulated it so the sound came either before or after the moment of impact. And the interesting thing there is when the sound was lagging, it was still integrating, even though when it led the moment of impact, it didn't integrate when it led with the same amount. And I think it's because in our world, sound travels slower than sight, so we're often presented with situations where they come from the same source, but the sound is later. I mean, not usually by a huge amount. The strange thing was there we found 400 and 700 milliseconds after impact, we were still getting integration, which is way bigger than the normal window that we'd find. But I think the key difference is you have like a second of the guy rearing up to go hit, and so you have this very strong prediction of when that moment of impact is going to happen, and also a very clear visual that it is an impact event. And so I think when all those cues for unity are firing at once, it widens the window there. But yeah, both modalities matter. I'm just more interested in the sound.
Have you tried introducing a delay between the impact and sound? Sorry, visual and audio?
Yeah, so that's what we did, where we had the sound come after, like you saw him hit it. Yeah, and then it works fine. But if you move it forward by the same amount, it goes away. Yeah.
It reminds me of when I studied the image study, somebody did visual experiment looking into the auditory cortex brain response, just showing the hammer hitting the surface and no sound.
Huh.
And the point of impact is trigger point for the evoked responses analyzed, and then auditory cortex have the response into that. So that's a very small paper, but that's
Who did that? Who did that study?
I can.
Yeah, I'd be very interested in seeing that. Huh, that's cool. Oh, yeah.
I was so reminded of a study. This is a pretty old study. I think it was done at MIT. I couldn't tell you who. But it was called sound of bouncing. It was the sound of crashing or something like that.
Okay.
The sound of breaking, sorry.
Okay.
Related to this hammer. But it's a study in identifying the process of sound production.
Okay.
It's about bouncing, and breaking and uncovering the source.
Sound of breaking, that's the name of it? or something like that.
Something about bouncing versus breaking. And
Was it with the bottle, the Warren and Fairbrook?
I couldn't tell you.
Okay.
I can tell you it's, could be 30 years ago, for I know, 20
Okay.
years ago.
Yeah, there was one in the 80s that I know about with a bottle bouncing, whether it broke or fell and whether it bounced.
That might be the one.
It might be. Okay. Yeah, it was one of the early ones that I'm aware of, and it's
Yes.
it's interesting.
And then they study those kinds of-
Yeah, I mean, I think it's such an important point, and that's why I think the Gavra stuff is so interesting, because this is like 1993 he wrote that, and I think all of his points apply equally well today, which is both interesting and also sort of unfortunate at the same time. And I actually, a reviewer suggested that one day when I was submitting a paper on something else, and I looked it up and I was like, oh, this is great. Like all these things that I thought I had that were new ideas were like clearly articulated about 20 years beforehand. So yeah, I think the sources are a very important thing.
Thanks, Dr. Schutz.
My pleasure. Thank you for listening.
That's the last conclusion this term. But if anyone wants to sign up for stuff for next term, I'm going to send out a note soon, or someone, whoever is going to send out a note soon, and ask everybody to sign up for additional spots and stuff. Okay.
Thank you for your detailed questions.
And